All right, let's see if we can wrap this chapter up here. We're gonna do some quiz questions. We'll finish up chapter 5 for sure. And then the OWL part 2, chapter 5 is Friday night. The quiz is Friday night. The test is a week from today, right? 1 week from today should be the test on chapters 4 and 5. So 4 and 5 only. We'll be talking about 6 today. Now, the learning guide, the next learning guide is actually 6 and 7 together as one. So it's not so bad. I mean, it's actually, there's 2 chapters I put together. So if you have access to that, hopefully, you probably have access to that. You do have access to that. You hopefully have that with you, or you have an electronic version. Now, for the test, what I would suggest is you already have, after today, you're going to be able to finish up 5. We got a few quiz questions to finish up. Go back and start looking into chapter 4. You have the quiz answers. Start redoing the problems from chapter 4. You want to look at the quiz. You want to redo the problem from scratch. Now, remember, this is not studying for your test. There's no way this is going to work. This is just not studying for your test. I guess I forgot one other thing. Huh? You have to, from scratch, paper, pencil, go through lots of paper. You want to look at a question. Oh, it's in grants. Well, I know I got to get the moles. Get the moles as fast as you can. Then go from there, right? Because if you're not given moles 99 times out of 100, you got to get the moles. Once you get the moles, then you can maybe see if moles are somewhere else, or maybe it's in molarity. You're going to cancel out moles, right? But it's an imperative. You have to start studying for the test now, not the night before. So, and the questions that maybe take you longer, you struggle with, then you want to do those more times, right? But maybe you can make a check mark on the side of the questions, because the test is going to look, my test questions should be similar to quiz questions. I might pull a few from OWL, but they do look similar to the quiz. And it makes it fast and efficient to do the quiz questions. Okay, and then after Friday, you're going to have chapter 5 answers. So starting Friday, Saturday, Sunday, I don't know. I used to take Fridays. Fridays were off limits for schoolwork for me. So I don't know. You need to take a day as well. But Sunday night would be big to do chapter 5, right? And then Monday night. But all right, let's look at these quiz questions here. So chapter 9, we laid this out in a previous class. We are solving this for the mass of the ice. So there's a couple ways to solve this, but we want out of this, we're putting ice at 0 degrees into 1,800 grams of water at 80. We want the final temperature to be 10. So for this problem, we know that our water here is going to lose heat. It goes from 80 to 10. So that's MC delta T. The first thing we need to do is we need to melt the ice. So that is the mass of ice times the enthalpy of fusion for ice. And then once we melt that mass of ice, we're going to have liquid water at 0. We need to get that liquid water up to 10 degrees. So it's the same mass. This is what we're looking for. So one way to do this would be to factor M ice, the mass of ice out. Otherwise, we could put in our enthalpy of fusion here. I would do it in joules. We could put our enthalpy of fusion in and combine these masses then. But eventually, we got to get the mass of ice out of this, and this does work. It looks like this answer here is coming out in grams. If I look at my units, I've got grams. So your mass might come out to be grams, and it looks like we've got to convert it to kilograms. 14, 15, okay. Let's see what we got here, 14. Okay, so in 14, we have the enthalpy change, delta H, for the following balanced reaction is 33.3 kilojoules per mole. This is a positive number. This would really be over here, 33.2 kilojoules per mole, plus how much heat will be absorbed by the reaction of 1 gram of nitrogen. Well, here's my connection. I've got grams here and I've got moles here. So the very first thing I'm going to do is I see grams on this page. I'm going to convert it to moles. So we've got 1 gram of nitrogen. And nitrogen is, each nitrogen is 14.01. So 28.02 grams of nitrogen, 1 mole of nitrogen. Then in this reaction, we need to look at the balanced equation here. And there is a 1 here, right? So it's this amount of kilojoules. This amount of kilojoules is for 1 mole of nitrogen. So this is correct as is. We can put this in 33.2 kilojoules per 1 mole of nitrogen. And we're verifying that this matches right here. So we get all done, grams, grams, moles, moles. Okay, now it looks like 15, 16, 17 are Hess's law. Now for lab that starts today, you are going to do a Hess's law. And remember, I told you previously, make sure I got my right one to roll on. Yeah. So we started Hess's law, or really for lab today, It's really reactions that are too slow. Do a Hess's Law problem today, you'd have to pack a lunch and bring a sleeping bag if we waited for that actual reaction to be done. So we're going to combine two reactions for lab today. We have to figure out, we want this reaction, so I would grab a highlighter and let's see what we've got here. We've got carbon monoxide here, and we've got carbon monoxide here. We've got carbon dioxide here. I'm going to put that in a different color. And we've got carbon dioxide here. And then we have oxygen. I'm looking at my carbon monoxide, my yellow first. We need to do what right away? We need to take this, this is what we're trying to achieve, right? This is what we're trying to achieve. We need to take this reaction in, reverse times 2, correct? Because of this 2 right here. So we should drop this one down as reverse times 2. And that would give us our 2 CO gas, 2 carbon solid, 2 times 1/2 O2. And if we did reverse times 2, the reverse is a sign change, right? The reverse is a sign change. So instead of getting 111 kilojoules, it's going to be positive. So it's going to be 2 times, I'll put a plus in here just to make sure we did it, 111 kilojoules per mole. So that gets me my 2 carbon monoxide. What about the other reaction? What about this one? I'm specifically looking at the carbon dioxide. Leave it the same, but multiply by 2. Because we have a 2 right here, correct? Let's see if we can bring it down. We can just go times 2 maybe, huh? So if we go times 2, we're going to have 2 carbon solid plus 2 O2 gas. Get 2 CO2 gas times a negative 393. Now, at this point, you're looking to cancel things out, and this does work. You can draw your line. Whatever we didn't highlight here has to cancel out. So for sure, these carbons are gone. 2 carbon solids and 2 carbon solids. Those are going to cross out. Times 1/2 is 1 oxygen here. With 2 oxygens here is going to leave me 1 here, right? So I can cross this out. This is a 1 oxygen. 2 over 2 is 1. 2 times 1/2. That's 1 oxygen here, but 2 here. So I can eliminate this, and I can change this to a 1. And that will add together. That should work. Let's get 16 highlighted here. So 16, we've got a nitrogen, one nitrogen there, one nitrogen there. I like what I'm seeing. So right now I'm thinking we just leave this reaction alone. And oxygen. I'm going to do my nitrogen monoxide next. So we've got 2 NO gas. Got 2 NO gas right here. I like what I'm seeing. Then I will do my oxygen here. So what do we need to do? We're going to leave reaction 1 alone, right? It looks like we just got to reverse this one, doesn't it? Just reverse reaction 2, and I think that should fall out. $17 we have not done yet. We'll cover 17 today. Cover 17 and 18 today. Okay, again for lab, we're going to do, starting this week, starting today, it'll be a Hess's law. You're going to add 2 reactions up. You're going to measure the heat for that reaction. And you're going to have to reverse one of them. It'll come out pretty nice. It'll come out pretty nice. Reminder, if you're in my lab, I did the last lab by percent error and I didn't really put any comments, but now that everybody's done with it and it was due, actually it's due Sunday for the Monday lab, so I can't email out the answers, but obviously if you got close to 15, your percent error was pretty low. So I'll send an email out again. I just did the percent error for all of yours and I didn't put down much comments unless you had sig figs on it. So I will get that out. Okay, any questions before we finish this up? All right, let's finish up then. We got a little bit to finish up and then we are done with chapter 5. So last time we met, we did a whole bunch of Hess's law problems. And 3 equations here. So now we've got one more thing that we are going to do according to heat. And that will finish us off. Okay. A quick comment. I think the lab see. Yeah. This is so silly, but I think in the lab write-up, it does the enthalpy. It just puts R for reaction first and then the H. It's the same thing. The R is switched around, but it is the exact same thing. Okay, now we are going to do what's called the standard enthalpy of formation. And that is, it's the enthalpy change for a reaction in which exactly 1 mole of pure substance is formed from free elements in their most standard states. So if you were trying to make water from hydrogen and oxygen, now the enthalpy of formation values for elements in their standard state is 0. It doesn't take any energy to make oxygen. We can take it right out of the air. It's already made for us, right? Carbon, graphite. That is the element in its most standard state. The enthalpy of formation values to form 1 mole of it is 0. So this little circular, looks like a temperature, is identified standard conditions of 1 atmosphere pressure, 1 molarity solutions. F stands for formation. So delta F, again, the enthalpy of formation to create an element in their standard states is 0. Okay, so here's some enthalpy of formation values. There's a table in the back of the book, I'm sure. So the enthalpy of formation for liquid water, negative 285.8 kilojoules per mole. If it's solid, negative 241.8. Just a single oxygen, plus 247.5. Oxygen gas, 0 again. Most enthalpy of formation values are negative, indicating the formation from the free elements are exothermic. So how do we calculate this out? Well, and why did I leave a big gap here? I don't know. Here's how we do it. What does this thing right here mathematically mean? This is a summation, right? This is a summation. This is our moles. And we want to sum up the products, the energy to make the products minus the reactants, and the moles will matter. And the best thing to do is just dive right into an example problem, right? Dive right into this example problem here. First of all, we know that we have reactants on this side. And we have product on this side, right? We know that. Okay, now we got to sum up products minus reactants. Now here's our values for everything. To form HNO3 aqueous, negative 207.4 kilojoules per mole. Nitrogen monoxide, gas, 90.25. NO2 gas, 33.2. Water liquid, negative 285.83. So it's going to look like this. We are going to do products. So I'm going to do a bracket here. Products. We got to start on the product side. So we start on the product side and have 2 mole of HNO3 aqueous. And to make HNO3 aqueous, we've got the value right here. That takes negative 207.4 kilojoules for each mole. So on our product side, we're making 2 moles of HNO3. We have to sum up our product side, so we're going to add one mole NO gas to make that 1 mole of NO gas. It's 90.25 kilojoules per mole. So I'm going to close this up. This is my products, right? Products. I'm going to put a big subtraction here. It's products minus, to sum up our products. We just summed up our products. I'm going to put a huge subtraction here. Products minus reactants. We do the same thing for the reactants. So I'm going to go exact same thing. I'm going to make a left bracket, and now I'm going to do my reactants. And I'm side. Three moles of NO2 gas. The idea, I don't know if I can, I guess I can still getting to the point where the more arrows might make it uglier. NO2 gas, 33.2. Gas plus here's my 1 mole of water. H2O liquid. And then my H2O liquid is negative 285.83. So all of this is my reactants, right? Products minus reactants. I don't know. Those arrows make it look uglier to me. All right, let's grab your calculator. And you could use parentheses in your calculator. Let's see if we can get one number. I'm going to put my equals. I'll put my equals in blue, I guess. Let's see if we get one number out of that. And I did put the parentheses in there where I had my brackets. I have my minus sign right there. See? That is correct. -1, what in that? It's not focus, it's reflecting. -138.32, anybody? Yeah. Should be right. We should get -138.32. Sig fig wise, it'll only be through. We only have we don't have a double decimal place on everything. -138.3 kilojoules. Or negative 138.3. All right, let's do one more. Next page. Standard enthalpy of formation for the following reaction was found to be, we've got the answer this time. And it says, what is the enthalpy of formation for NO2 gas? NO2 gas is right here. Now, there's a value missing here. We have NH3. We have H2O. Why don't we have H2? Because the enthalpy of formation for H2 gas should be what? 0. All right, let's see. Let's lay it out exactly like we did before. So we're going to do products minus reactants again. I'm going to put a red left bracket. Again, we're starting on our product side. Start with this. Got 2 mole of NH3 gas. And for NH3 gas, negative 45.91. Back off on my arrows, huh? Plus water's here. Ugly, some ugly writing. Wow. And my value for H2O gas is negative 241.8 kilojoules per mole. There's my 2 products, right? Summation of my products, big subtraction, minus my reactants. So I'm going to go left bracket again. And it is 2 mole of NO2 gas. This is what we're looking for. We're looking for X right here. So we don't have that value for NO2 gas. Plus do my last arrow. Seven mole of hydrogen. Zero. Now, we know what that equals, though. That equals negative 1125.2 kilojoules. So I think we'll grab our calculator and just kind of get this products right here at least, huh? Let's get our product number. Let's get our product number. Do I want to put it in React? I guess I will. So just my product up there, let's get that value. I can't get any value if I don't push my calculator on, power it up. Wow. One zero 1059.02. Yeah, on my product side. Minus, what do we got here? Minus, well, that's just it. Minus 2x equals negative 1125.2 kilojoules, right? I put those big ugly brackets in, but I surely didn't need them. Now, wait a minute. Okay, yes. I almost had to distribute that negative, but we're good. Minus, here's my minus 2x. It's just minus 2x. Now, what I would do, I would just do cheater's math. And I'm going to throw this minus 2x to the other side, make it positive. I'm going to put this negative this side, make it positive. That's essentially the same thing, right? Those math people make it so complicated. So then we're going to end up with minus 1059.02 kilojoules plus 1125.2 kilojoules. Then 6.8 kilojoules equals 2x. That shouldn't be too bad. So I did mess up. But we can answer it next time. 17 still is a Hess's law. And 18 is what we just did. Should be entropy of formation. Yeah. F here. There's only one problem like this on the quiz, like what we just did. OWL does have you solve one of these for X like this. So I think this gets you to the last section of OWL. Okay. All right, so let's so that's it for chapter 5. So I'm going to file this. Friday night finishes the requirement for OWL is due Friday night. That take-home quiz there is due Friday night. Of course, Thursday, right? And again, the test should be 1 week from today. 1 week from today. Okay. Now. We are going to look at chapter 6. And I filled more things in. Tried to straighten things out every time I use this. So I'm not going to assign you any chapter 6 quiz questions today. You finish up everything from the last unit, but let's just page through this, see where we're going to go a little bit here. So in chapter 6, we're going to talk about electromagnetic radiation in waves and frequencies. And some calculations of how much energy, energies for AM radio, energies of electrons. We talked just a little bit about the photoelectric effect, spectrum, colors. And then we start talking about the energy it takes to boost electrons farther away from the nucleus in a higher energy level, and it drops back down to emit that energy. And we try to explain these colors that we see when the electron drops back down to level 2. Try to help you out with the OWL questions here. So this is an exact OWL question, word for word. And then chapter 6 continues with electron configuration notation and quantum numbers. And it does the shapes of orbitals. Probably seen diagram that look like this with the off-ball principle and how these electron or orbitals fill. We are going to do electron configuration notation. So this is chapter 7. So this is where it rolls right into 7. We'll talk about valence electrons. We'll fill this chart out for orbitals. We will talk about and do quantum numbers. Some OWL questions again on quantum numbers. We'll fill in this blank periodic table. Do not fill any of this in ahead of time. Electron configuration notation of ions and paramagnetic and diamagnetic. And another alt question at the end. So again, this is 6 and 7 together. And I don't think there's 2 parts. I think chapter 6 in OWL is 1 part, and I think chapter 7 in OWL is 1 part. But I'd have to double check. Now, this is the recording. So you could look at this ahead of time. I did go in and link this. So if you look at this recording from a previous semester, I don't remember if it was last semester or what. But then I also have YouTube videos here. So if you grab this and download this to a Word doc, all of these hyperlinks you can just click on, right? So, and this is a really good, some of these I am going to play in here. So, this is kind of my learning guide, my mini textbook. I put this together. I use resources from our textbook, from the internet, from OWL. So, all right, let's talk about this. Let's go to this page right away here. Actually, yeah, let's go to this page. So we are going to talk about energy and electromagnetic waves. Now, what are electromagnetic waves? Waves that travel at the speed of light, right? So radio waves travel at the speed of light. Now, this distance here, let me turn this around. This distance, wherever a wave repeats itself, is the wavelength. We can get a distance. Now, the symbol for wavelength is an upside down backwards Y. It would be this distance. Wavelength. And the frequency then is how many waves per second. How many waves per second is our frequency? So we describe it by the wavelength, the distance between it, and how many waves per second come. So you could be laying on your inflatable in the lake, and a jet ski comes by. It sends a wave towards you. Okay? So you're going to bounce up on that wave. If a second jet ski comes by, you're going to get another wave. There's another description for a wave, and that is the amplitude. That is just the height, how much energy that wave has. So now if a big boat comes by, it's going to send a wave towards you with a heck of a lot higher amplitude than that jet ski. Then if you go this way, frequency increases. This would be like a jet ski coming by maybe every second here. But then if you're going both directions and you got 3 jet skis coming by per second, you're going to get bounced around more and more and more. So as I go to the right, we get more waves per second. So we have radio waves here again. These are long wavelengths, but you don't drive down the road listening to 100.7 or 104.5 or 92.9 or whatever it is and say, hey, boy, I can see that radio wave hitting my antenna. I can just see it come through the air. I'm glad it's coming into my car, right? You don't do that. Microwaves, you don't hit that microwave button and, oh, I see those waves making my food hotter, right? You don't see that with the naked eye. This infrared radiation, this is your IR remote control. You don't hit the button towards the TV and say, oh, I see that beam going towards the TV. I'm glad that beam changes my channel for me. You don't see that. But finally, you can see visible light is just this tiny region right here. very, very small portion of this entire electromagnetic spectrum. Because if you keep going, ultraviolet radiation, you know, lay out in the sun and say, ooh, I can see those waves whacking me. It's burning me. I can really see that wave hitting me, messing up my skin. You don't see that. Take x-rays, you don't see those. So you have different wavelengths and you have different frequencies. It is no different. We could do something like this for sound. And for sound, you could have down here, you would have your bass sounds. Then you would get to your mid frequencies and then you'd hear high frequencies, right? And after high frequencies, you don't hear them. What can hear high frequencies? I know dogs can, right? What can hear lower frequencies and what your ear can hear? Whales and lots of things in the ocean, it's low frequencies. So we could do the same thing for sound that we have here for electromagnetic waves. Now, let's talk about this. As we go up here, red, orange, yellow, green, blue, violet, they took indigo out. Red light has a wavelength. This is my wavelength. NM, what does NM stand for? MM would be millimeters, N is, so this is nano. So this would be the same as 700 times 10 to the minus 9 meters, nanos to the minus 9. As I go up, notice that as I go up this way, from red to violet, my wavelength goes down to 400 nanometers. So here, upside down, backwards, Y is my wavelength. This would be 400 10 to the minus 9 meters. Now, Owl starts out and just does a lot of questions that all relate to this. As I go from red, orange, yellow, green, blue, indigo, violet, what's happening to my wavelength? Wavelength is going down, right? Wavelength decreases. But what's increasing? Frequency increases. Now, here's the key that I'm going to put this in red. Frequency and energy go together. So if frequency increases, higher the frequency, the higher the energy. All right, now let's go back to my first page. It's kind of an introduction now. We know that as we go down here, we've got long wavelengths, low frequency. Let's go to page 1 here. Okay. For all of this, for all of our waves, we know that C is equal to lambda, and I'm doing frequency as F. You'll see that I've changed this up a bit. speed of light. And we're going to round this to 3 times 10 to the 8th meters per second. Wavelength. Years. Frequency. Frequency is 1/seconds, which is equal to hertz. HZ for hertz. It's not just a rental company, rental car company. It's frequency, hertz. Okay. So here's a pretty good introduction here, Professor Dave does, but otherwise, 1864, James Maxwell developed his theory of electromagnetic radiation and showed that light was the visible part of a vast spectrum of electromagnetic waves. That's what we looked at. Visible light is just a small portion. These waves travel through a vacuum at a constant speed, 2.998 times 10 to the 8th. We're going to round that to 3. Waves are characterized by upside down backwards y, which is the Greek symbol lambda, which is our wavelength. And that's going to be in meters. And then this cursive V called nu. I'm doing F for frequency. I cannot do this symbol. You're going to see F. F. Frequency, 1/seconds for the unit, 1/seconds. And then amplitude. Now, again, you could equate all of this to sound. So you hear sound, don't write this down, and maybe you've got speakers that might look something like this. Might say, well, why is there 3 different size speakers? Sound travels the same speed, correct? Sound all travels the same speed. Well, this we say is your base speaker. This is going to handle maybe 20 hertz up to maybe 800. Now realize these speakers are they suck in because of an electromagnet. You've got a magnet back here. You've got this speaker cone system. If I can draw this out real quick. Prettiest. Not the prettiest at all, but you've got electromagnetic wires wrapped back here. And what happens is when you turn up the volume, this electromagnet kicks in more, it sucks the speaker in and the speaker flexes back. When the speaker flexes back, it pushes the air molecules together when it flexes back. It's no different than a drum head. If you take a drum, and if you hit this head, it flexes back. And then it's going to come back the other direction, and it's going to push air molecules together. The speaker sucks in, you get almost a vacuum with hardly any air molecules, comes back out, and it pushes it together. Well, this big bass speaker 100, it can't flex back fast enough because it's too big. You can't push 1200 hertz into this speaker. It's going to sound like crap. So this flexes back. This big speaker can flex back 20 times a second or 800 times a second. After that, you got to go to a smaller cone because it can't flex back fast enough. Then you would have what's called your mid-range speakers here, and they'll maybe take 800 hertz to, oh, let's see, I'll take 800 to probably 10,000 hertz, 12,000 hertz. So these can flex back from 800 to 10,000 times a second, and then you got to go smaller because these will flex back from 10,000 hertz to 20,000 hertz. That's the maximum a human being can hear, from about 20 hertz up to 20,000. This is going to be really, really high. This is going to be really, really low. And we know that dogs can go over 20,000. And ultrasound is below this. We know that other animals can hear below 20 hertz. But again, it all travels the same speed, but you have different frequencies. So it's no different than light. It has different wavelengths, different frequencies. So I did this. I said, calculate the equation to calculate the speed of light. C is equal to lambda f. I'm changing this to an f. Let's pretend the speed of light is 24 meters per second. Complete the table. This is in meters per second. My wavelength is in meters, and my frequency is 1/seconds for units. So these two multiplied together, I got to get 24 meters per second. We're just pretending the speed of sound is 24. It's definitely not 24. So if my wavelength is 2, what's my frequency? 12. If my wavelength goes up 4 times, what does my frequency do? It goes down to 3, correct? If you increase your wavelength, you're going to decrease your frequency because you cannot change the speed of light. If my frequency goes from 3 to 6, my wavelength goes down to 4. If my frequency goes up to 24, my wavelength goes down to 1. If I decrease my wavelength to 1/2, my frequency goes to 3/8. Okay. If you adjust one, the other one has to make up for it. Okay. The electromagnetic spectrum consists of very small wavelength, high frequency waves called gamma rays. Gamma waves, way up here, gamma, high frequency, small, short wavelength, up to long wavelength, low frequency wave called radio waves. Way down to bottom, long radio waves. Again, the work of Maxwell showed visible light is only a small portion found between, light here is found between infrared and ultraviolet. Ultraviolet, infrared. To give you an idea of the difference in wave characteristics, you may listen to 92.1, the X. Anybody listen to the X? What? Nobody? Nobody said, you got a big shaking hand back there. Sometimes I just got to turn the X on. I got to tell you, if I'm listening to country, I just got to have a change because when I listened to country, I picked up my girlfriend in my pickup truck. My dog jumped in. We drove down to the lake, got a beer, and then we parked next to my tractor. So I got my pickup truck, my tractor, my girlfriend, my beer. I'm fishing. I got a country song, right? And sometimes I just need a break. You turn it to the X, which is kind of the exact opposite, right? So the X is kind of, it's fine. So you may listen to the X, 92.9 on the FM station or 790. Now look at the difference. There's an M here on FM, and on AM, there's a K. So you got 92.9 megahertz on an FM station or 790 kilohertz WAYY for an AM station. Or you may use 4G cell signals at 700 megahertz. The FM stands for frequency modulation and the AM stands for amplitude modulation. The frequency in hertz of 92.9 is 92.9 times 10 to the 6th. That's mega. And the frequency in hertz for 790 is times 10 to the 3rd. This is my kilo. And this is my mega. Again, kilohertz, megahertz. Therefore, the wavelength of 92.9 FM, we've got to calculate it. So let's go down here. We're going to calculate. We know that C is equal to lambda F. So we have our frequency. We're going to calculate our wavelength. So C divided by our frequency should be our wavelength, right? So 3 times 10 to the 8th meters per second divided by a frequency of 92.9 times 10 to the 6th hertz gives me my wavelength. Oh, I didn't put in times 10 to the 6th. 3 to the 8th divided by 92.9. Oh, I put it in wrong again. To the 6th equals. All right. This gets us 3.23 meters. Well, let's get it in feet so we can relate to that. We know that 1 meter is 3.281 feet. Times 3.281, 10.6 feet. So the wavelength of the FM 92.9 is 3.23 meters or 10.6 feet. That wave is going to repeat itself every 10.6 feet, but let's see what AM does. So the same thing for AM. Three times 10 to the 8th meters per second divided by 790 times 10 to the 3rd. Oh man, I can't use my calculator today. You get 300, about 380. Okay, so 380 meters. And if I do the same thing, 1,240, 1,250 if I rounded it to 3 sig figs. 1,250 feet. Almost a quarter mile. So there is a big difference in wavelengths and frequencies for your radio stations you can tune into. Which one of these goes farther, AM or FM? AM by far, but it gets a lot more interference. So we're going to be turning over to 5G coming up. That does not go very far. So 5G towers have got to be put up all over the place. Okay, so now let's go to this diagram here. And on this diagram right here, we should do this. We have radio wave. We know AM down here. I should put this in red. And then FM has a higher frequency. AM, FM. In fact, I think my next diagram, I have it on there that way. And it does. This is the same diagram on the next page. It just lays it out a different direction. Again, energy increases, frequency increases. They go together. Energy goes with frequency. But what's going down that way? Wavelength decreases, right? Okay, let's call that a wrap. Don't anybody steal my song now. Not that far off on some of those country songs, am I? Huh? My girlfriend, my pickup truck, my dog, my tractor, my beer, fishing pole. What's that? Girlfriend, oh, that's right. New girlfriend. Old girlfriend, new girlfriend. Should I state it that way? Old girlfriend, new girlfriend? Grandma, grandma.